Let's talk about system design. It's kind of the hidden architecture that powers our entire digital world. I mean, from the second you refresh your social media feed to the moment you click buy on something online, you are interacting with these incredibly complex, massive systems. And just to give you a sense of the scale we're dealing with here, think about this. A platform like Twitter has to process over 6,000 tweets every single second. That's insane. That's over 350,000 a minute, and about 500 million tweets every single day. So you gotta ask, how is that even possible? Well, it's not magic, that's for sure. It's the result of a discipline called system design. And really, at its core, system design is all about solving a series of huge, epic challenges that pop up when you go from just a few users to millions or even billions. Okay, so let's dive right in with the first major hurdle every popular app has to clear. How do you handle a massive, just overwhelming crowd of users? Because one single computer, yeah, it's not gonna cut it for long. So when your first server gets totally swamped, you've basically got two choices. Option one, make that single server way stronger. Give it more RAM, a beefier CPU. We call that vertical scaling. Or option two, you can add more servers to the team to share the work. That's called horizontal scaling. And for pretty much every huge service you use today, horizontal scaling is the name of the game. It's just way more flexible and you don't have all your eggs in one basket. Right, but if you're gonna add more servers, you need a way to manage all that incoming traffic. And that's where a load balancer comes in. You can think of it like a digital traffic cop. It stands there and intelligently directs all the user requests across your whole fleet of servers, making sure no single one gets buried in work. It's what keeps the entire system feeling fast and snappy. All right, the next villain we have to take down is delay, or latency. Because in the digital world, every single millisecond counts. A slow-loading site can mean losing a user forever. Speed isn't just a nice-to-have, it's the feature. So one of our key weapons in this fight for speed is something called caching. And the idea is actually simple, but it's brilliant. It's all about storing a copy of the stuff people ask for all the time in a temporary, super fast place. So instead of going all the way to the main database every single time, which is slow, the system just checks to cache first. It really is like checking your fridge for milk before you make a whole trip to the store. Now check this out, because this is where it gets really powerful. We can take that caching idea and make it global. So let's say your main server is in Finland. If a user in Mexico wants to see your website, they might have to wait 3, 4, even 5 seconds for it to load. In internet time, that's an eternity. But with a content delivery network, or CDN, we put these little caches all over the world. So now that user in Mexico grabs the data from a nearby server and boom, the load time gets slashed to under a second. Game changer. Okay, let's get to our final challenge, which is all about planning for the one thing you can be absolutely certain of in any complex system. Things will break. It's inevitable. Hardware fails, networks go down. A truly good system isn't one that works perfectly all the time. It's one that's resilient when things go wrong. Our main defense against total failure is called replication. It just means we don't keep only one copy of our data. We keep multiple identical copies spread out across different servers. It's kind of like having backup diaries. If one server and the diary on it suddenly bursts into flames, another one is right there, ready to take over instantly. Most of the time, users won't even notice anything happened. But, and this is a huge but, this is where things get really complicated. Trying to keep all those copies of your data perfectly synchronized across different machines, especially when the network gets flaky, that creates a fundamental, really difficult problem that's right at the heart of designing distributed systems. And this difficult problem leads us straight to a very famous principle in computer science. You might have heard of it. It's called the CAP theorem. And what it does is present every system designer with what feels like an impossible choice. So here's what the theorem says. Any system that runs on more than one computer has 3 things it really, really wants to have. But, and this is the killer part, you can only ever guarantee 2 of those 3 things at the exact same time. You have to pick. First up, the C is for consistency. This is a guarantee that whenever anyone asks for data, they get the absolute most recent, up-to-date version. The perfect example is a shared Google Doc. When one person types something, everyone else sees that change instantly. The document is consistent for everyone, everywhere. Next, we have A for availability. This just means the system is always on and will always give you an answer. It might not be the most up-to-the-millisecond data, but it won't just fail on you. Think of an e-commerce site that's never closed for business. It's always available.
And the final piece of the puzzle, the P, is for partition tolerance. This is the system's ability to keep chugging along even if some of its servers can't talk to each other anymore, because the network between them broke. It's like a company with two offices. If the phone lines get cut, both offices can still serve their local customers just fine.
So here's the crucial part, the big takeaway. In any real-world system, network failures are just a fact of life. They're going to happen. That means you have to design for partition tolerance. It's not optional. And that forces you to make a really tough trade-off between the other two, consistency and availability. You have to choose which one you care about more. And you can see this choice everywhere. A banking system? It's always going to pick consistency over availability. It is much, much better to temporarily not let you make a transaction than it is to show you the wrong account balance. Financial accuracy is everything. But on the flip side, a social media feed would much rather be available. It's better to show you a post from a few seconds ago than to show you nothing at all, right? And that really brings us to the core of this whole thing. At the end of the day, system design isn't about chasing some kind of theoretical perfection. It's about mastering the art of the trade-off. We even have a language for this. We talk about a system's reliability in nines. So the absolute gold standard is 5 nines, or 99.999% availability. You know what that means? It means the system is designed to be down for just over 5 minutes in an entire year. And getting that last 9 of reliability, that involves incredibly complex and expensive engineering decisions. So, you see, great system design isn't about finding some perfect one-size-fits-all solution. It's about deeply understanding what really matters for your specific app. Is it ironclad accuracy, or is it being online no matter what? It's about making smart, informed compromises to build the right system for that specific job. So, it all boils down to one question. What trade-offs would you make?